I'm Ralph. I'm a contractor from SRI, which is down in Menlo Park. Used to be called Stanford Research Institute. And Paul Berner is even worse. He's a consultant. We have cut what used to be a set of slides that ran about 240 down to 158. So we hope that it'll be a little more relaxed, a more even pace, and we will have a lot of room for questions. You've all read this, what the tutorial is about. Otherwise you wouldn't be here. Prerequisites for this tutorial are almost nothing, although it'd be nice if you knew something about SEDRIS. I hope you have an appreciation at the end on how complex this whole subject is and how important it is. On this thing, if you've taken high school algebra, you're qualified, I would say. Maybe a little calculus. But we're not gonna be focusing much on the mathematics, more on the physics of the situation. I'm going to make a little introduction here. Paul's going to come up and talk about basic terminology and mathematical infrastructure. Then I'm going to talk about the map projections, what an augmented map projection is, something that you may not have heard about, and a little bit about distortions. Talk about models using SRF, and by that we mean things like the geoid, pressure models, equipotential models, and that sort of thing. We're going to talk about spatial operations. Operations includes the class of things you normally call transformations or conversions, but we also have included things like computation of azimuth angle, geodesic distance. Those are all operations on spatial reference frames and within spatial reference models. Talk a little bit about quality assurance, concept management. I'm going to hop up and talk about computational considerations. They won't let me use my favorite slide in this class, which is Vince Lombardi saying winning isn't everything, it's the only thing. My slide says efficiency isn't everything, it's the only thing. And why do I say that? People throw rocks at me for saying that. But the fact is, almost every model and every one of the implementations of spatial reference frames is compromised in the name of computer efficiency. When you dig, you'll find all the models are compromised. And we don't have to do so much of that anymore these days. Machines have gotten a lot faster, and algorithms have gotten a lot better. We're going to talk about a little bit about how you select a spatial reference frame for the actual intended use of this material. We're going to talk about what we've done for SEDRIS and something about the implementation of the spatial operations. Now, the term SRM is a dual-use term here. It's a general concept, and there are two aspects that we're going to talk about, and sometimes it'll be hard to distinguish which we're talking about. The first one is more of a formal aspect, which is the SRM as a international standard. This is a French contraction, but I'll read it to you in an interpretive way. International Standards Organization, International Electronic Commission, 18026 Spatial Reference Model is an emerging international standard. It's under development and is currently at draft 7. We attempt all through this tutorial to use the language of that standard. We're trying to focus on precise meanings of terms. And among the things you're going to find is we don't spell center the same way you spell center, or meter the same way you spell meter. So it'll be M-E-T-R-E. You'll see numbers with commas in them. But after all, we're in Canada. We fit right in, right? We promote consistency with other international standards. The efficiency and implementation issues involving algorithms are not part of a standard. Standard set, this is what it is. There may be a number of different implementations of that standard. You ought to be able to tell whether you met the standard or not, whether you conform or not, but how you do it is left up to the user. So that leads me into the other aspect of what we call the SRM, and that's the SEDRIS implementation of the SRM. So now we're talking about a real implementation. We are designing and have designed SEDRIS to be compliant with the emerging 18026 standard. Now, obviously, we're never quite compliant because the standard is changing. And in fact, in some cases, the implementation is in front of the standard. So we bounce one off against the other. Our implementation is application-driven, and the people who are the main users are the ones that kind of mold which direction we go in. We have a software architecture and a spatial operations API. Our algorithms that we've actually implemented are designed to be accurate, robust, and efficient. Now you'd say, well, that's motherhood. But when we first started this, we were using a lot of authoritative software against which we compared things, and we found that some of them weren't accurate and weren't robust, and none of them were efficient. And so we kind of aimed at that sort of thing. We'll talk about why the efficiency is important later. And we've done a lot of testing of the software. SEDRIS, as you've already learned, is got a lot of components and a lot of people are involved. And believe me, they do a lot of testing. So I'm first going to talk about interoperability. Some of the more rudimentary, I'm going to talk from a modeling and simulation aspect, but I will quickly tell you that what I say is also applicable to embedded systems, real systems, and lots of confederations of live, virtual, and constructive systems. Some people have models that just involve systems. This guy's got 10 times more forces than that guy, and so he wins, right? No. As the Turks found out when they took on Alexander. It matters where they are, what they are, and how they're applied. In addition to how many are there, we need to know where they are. That's very important. And a lot of the legacy simulations that we've dealt with, there is no environment. No direct implementation environment. The way you account for rain is you just make things move slower, but there's no actual environment. Finally, as we get into this more precise world with these better systems that we have, more precision location systems, we're able to define the environment fairly precisely and put the trees and the water and the terrain and that sort of thing into all of our models. The last little box over there says if you don't do it right, you can advantage or disadvantage a simulation. Now, the word interoperability was used here, and what we're implying is there's a confederation of things that talk to each other. If you have a single simulation that doesn't talk to anybody else, you may never know you have these problems. You can't tell. It's only when you start interacting with someone else and you can see something and they can't see something and you say, hey, there's something wrong here. Consistency is very important. Excuse me. And this applies to all kinds of models. You know what an aggregated model is? Something in which the elements of the model are groups of things. In a military sense, a division. Entity level models are where you model vehicles or people, individual entities. Constructive models are models that are more computer oriented. Some people have the idea that constructive models don't have humans in the loop, but they do. They're just supplying tactics at a different level than the virtual models. The virtual models have people sitting in simulators looking at wraparound graphic systems, and they are a tank driver or an airplane flyer or whatever. That's a virtual model. And of course, live really means simulated activities that are done in the real world. I mean, people don't shoot at each other in our tests, usually. Unless it's the Air Force versus the Navy or something, and it's a football game, maybe then there's a little hostility, but it's simulated operations, even though they're live. Well, why do we need one of these models? And I've kind of nattered at this, and I will repeat themes over and over because you need to hear them 3 times. Inconsistent models of the Earth and related coordinate systems are a principal reason why interoperability doesn't work. Just very simple. We need consistency so that we can have a reasonably level playing field. What does that mean? If I see you and I can interact with you, you better be able to see me and interact with me. And if that doesn't happen, and it's caused by the fact that you're in one coordinate frame and I'm in another, we're in bad trouble. To support meaningful, VVNA stands for verification, validation, and accreditation. Something that a lot of people forget about is you can't validate anything unless you have a ground truth model. And how could you have a ground truth model in 10 different coordinate systems and 5 different Earth models? You've got to have a consistent model in which you can do VVNA. I talked about how different Earth models change the representation of the environment in modeling and simulation. Dynamics is a subject near and dear to my heart. We'll expand on this in a little bit, but people are forever constructing non-real world coordinate systems and then pretending that Newton's laws apply in those coordinate systems, and they don't. And you can get in a lot of trouble that way. Then there's a geometric thing. That's what acquisition modeling here means. This is the can I see you, you see me, the line of sight problem. If you're in different coordinate frameworks with different representations of the terrain, you might get different I can see yous or not see yous. Did I mention runtime and efficiency? Almost every code you see has low-level approximations made to make the coordinate transformation run faster. Unfortunately, sometimes these are in there and you don't even know about them because some programmer put them in there and didn't tell you about them, trying to meet his speed requirement. We don't want to do that. That can introduce all kinds of other inconsistencies. One paper I wrote about 5 or 6 years ago changed the computational accuracy of geocentric to geodetic conversions from about 1 meter to 1 millimeter. Does that make a difference? Well, a geodesist might say, oh, well, we can only measure to 0.5 meter, so what are you worrying about? But a fire control guy, particularly a guy who shoots at tanks, is shooting at a target that's 10 centimeters high. You know what tank people aim at? They aim at the turret ring, big, long thing, but real thin. So a meter error in your fire control calculations is bad, bad, bad. So you'd like to have high accuracy. You want your operations to be lossless. You want to be able to pull data over and not lose anything, any content. You don't want to add anything either. The last bullet, I think, is very important. We have a tremendous nomenclature problem in the business. When I say height or altitude, what do I mean? Worse than that, when I say elevation, what do I mean? I'm doing some work for the Air Force right now at the Western Test Range. In fact, next week I get to go to the critical design review, and they have the word elevation scattered all through their documentation. You know what they mean? They mean an angle. If you go to a geodeser and you say, what is elevation? They mean mean sea level or orthometric height, one or the other, which are different but similar. They mean something like that. Quite a different concept. Geodetic height is not height. Height above mean sea level. What is mean sea level? terrain height, pressure altitude, etc. A tremendous inconsistency in nomenclature that we're trying to fix in the spatial reference model, and I'm going to guarantee you it's not easy to do. This is an international committee trying to settle on the meaning of the fundamental terms like this. Really difficult. Plus there's tradition. Each application domain means something else by that same word, and they don't really want to give up their position. When we're talking about simulations, I mentioned that the interfaces between simulations makes things tough. A traditional hierarchy of models doesn't work very well. I don't know if any of you have ever been involved in interfacing two simulations that are at disparate levels of aggregation. The interface there is called a armchair interface, because a fellow looks at the output of one simulation, turns and puts that input in another simulation, and then goes back, all the time interpreting the meaning of this thing so it can put it in there. Not very good, not very fast. A major problem is the inconsistency of Earth reference models, and the way the aggregation policies are handled makes a big difference. Now, it's a little bit easier, but certainly not easy, to interface entity-level models. So if you have a thing out there called a truck, it has a bumper number on it, and there's another truck over here, and they're operating on the same Earth model in the same coordinate system, you have a hope of being able to interpret between them, where are you questions. But if they're in different Earth models, you got a problem, right? I used to have some charts showing this Grand Canyon, that the interface between aggregated and constructive models is called the Grand Canyon. Aggregated models don't have bumper numbers. You don't know where anything is. Halves of tanks are killed. You know where the center of a gate is, but you don't know where the individuals are, and you don't know who's been killed and who's alive and that sort of thing. The reason I took it out is there's another Grand Canyon that's even bigger, much bigger. And that's the Grand Canyon between live and virtual and constructive. A huge canyon that a lot of people approach naively, and they don't really understand that there's a canyon. We cannot measure in the real world to the precision which we can compute in the simulation world. And you have to be very careful about that. And by the way, recent experience and old experience with test ranges, you would think that all test ranges would have the same Earth models. And in fact, they all have different Earth models. Now they're trying to talk to one another. And it's a real problem. I've already mentioned that beyond modeling and simulations, there are other application areas. Embedded systems just mean something like an airplane that drops bombs or navigates or does something. It's a combination of hardware and software. They have to communicate spatially referenced data, and it ought to be right. Test range operations is another thing. People are trying to get the test ranges to become a virtual range and talk to one another, but they all have different coordinate frameworks. And if you're going to do any of these things in a federated way, you need standards. What should an SRM have in it? Well, it's got to be complete. Got to use common coordinate frameworks that are commonly used. Needs to educate the systems developer, which is part of what this course is about, accuracy. Why do we need such high accuracy? Well, I've kind of hinted at it a little bit, but there are a lot of applications where you cannot tell whether you missed or not unless you have the accuracy. Now, it turns out that it's sort of pro forma to get very efficient algorithms that are very accurate. So we just set the accuracy requirement really tight to 1 millimeter, generally. Other people will ease that, but today there's no reason to do that because the runtime is the same. You don't gain much. You cannot have approximations made in coordinate transformations impact the validity of your result. You don't want that. You always want more performance. We are dealing with environmental databases that are gigabyte size, multi-gigabyte sizes, and some, in the case of a military application, some general is planning a war and he's in the middle of it. He gets word that, oh, there's a weather front coming, and I need to take all that data and reconvert it, rebuild a scenario. And by the way, I want that right now. Currently, the requirement's 72 hours, but you know it's going to be tighter than that as time progresses. So runtime is really important. There's a fellow named Jim Shiflett, who used to be Colonel Jim Shiflett, who ran the CCTT program, that used to complain to me all the time, these darn that isn't what he said, these darn coordinate transformations take 20% of my computer time. Now, how could that be? Well, it did. It doesn't anymore. We build algorithms in SEDRIS, and we're talking about implementation here, that are very accurate. Our goal is 1 millimeter position error. And we're going to talk about what accuracy means here in a minute, that are 2 to 10 times faster. I used to have 30 in there, but that's only in one case. Meaning of accuracy. Since there are geodesists in the room, and nobody's jumped up yet and said, what do you mean 1 millimeter? You can't do that. Well, we aren't trying to. In geodesy, you fit Earth models to sets of data. And you do that to provide a spatial referencing framework, something you can compare to. And there's a certain amount of position error you accrue by doing that process. And that's a major and difficult issue in geodesy. Is how good is your Earth model? How good is WGS84, for instance? We don't deal with that. What we do is we take the published Earth reference models, in this case, as being exact. So that's given ground truth. And we go from there and say anything you do after that, like approximations you make or round-off error propagation or any of that kind of thing, is our responsibility. And that's what we mean by accuracy. So we're excluding modeling error of the Earth reference model in this case. But you can still have inaccuracies. As some of you know, the coordinate conversion equations for some of the projections do not have closed form solutions. And this always comes up over and over in meetings. How many terms in some Taylor series do you use? If the Germans are there, they reference some German book that has this many. If tech is there, they have what they have. And there are various camps that have different representations of how many terms in a Taylor series. And I have never seen anybody do an error analysis saying, well, you need this many terms to get that accuracy, even though it's fairly straightforward. So that's a problem. Round-off error can be bad. We have some people that are naive about that and try to do computations in single precision to save runtime with numbers that are right at nearly the boundary of what you can represent in single precision. You want to be very careful about that. You could lose a half a meter if you use single precision with numbers that are the size of the Earth's radius. And then there is this ubiquitous practice of, I'll change the algorithm, make it simple. I won't take that many terms, I'll take this many, or I'll iterate once, or some other approximation. But the important thing is we exclude measurement error. Now, I said in the past we couldn't measure very well, but that's changing quite rapidly. You can get, and these are updated numbers probably, you can get absolute accuracies of about 21 centimeter. SEP means spherical error probability, the 90 percentile. So 90% of the time you're within a sphere of 21 centimeters size globally. If you want to work relative to a well-surveyed point like we have at Menlo Park, you can get centimeter accuracy in a region that's local. And of course, accuracy in real applications depends on how much money you want to spend on hardware and processing and computers and a lot of other things. There is a point here about in the real world, many applications use mostly relative coordinate systems, and I will talk about that later in a little more detail. But roughly speaking, if you're going to shoot an artillery shell over a hill at a target you can't see, you're totally dependent on absolute errors. But if you're aiming a deer rifle at a deer on the next hill, you don't really care what his absolute position is or yours. You're working in a relative system relative to you. We have some examples that address that later on. You have to portray both of these kinds of things in simulation these days. Mixing of live, virtual, and synthetic, I guess I beat that a few times. Go read Jerry Lucas' paper, which is published at CISO, and how important it is. Now, there's a special use of models and simulations that does cause some danger to people. That's mission rehearsal. And that's where accuracy has to be, really paid attention to, because if you're going to fly people in a simulator over terrain in the dark of the night and all that, and they're going to practice, it better be close to right, or they might get killed when they actually do it. So they have special accuracy requirements. Location's not enough. This basically says you got to know azimuth, you got to know range, you got to know a lot of other operational outcomes, and that location interconversions between common spatial frames that are used now don't always preserve these. We'll talk about that. Scope. It used to be the model simulations were done close to the Earth's surface. And you can see we're going up fairly high to the magnetosphere. That's where geosynchronous orbits occur, about 22.5 nautical miles. But this chart is rather a weak chart because we really mean a long way up, a lot further than that. In fact, we want to consider other objects like that's Mars in some polyconic projection form. The scope of the SRM is the entire solar system. So we're going to consider any real or conceptual object in the solar system. You're going to see some interesting terms. Instead of terms like geodetic, you're going to see celestiodetic. We're kind of reserving the word geo to mean the Earth, and celestio to mean something else, because there's lots of planets out there that are ellipsoidal in shape. This all requires a shared solution when you're going that far out. You really need to understand this concept, especially if you intend to interchange data not only in this country but internationally. And I already mentioned this is not unique to models and simulation. And so this is a worldwide problem. It's being tackled by ISO-IAC, Joint Technical Committee 1, Special Committee? Subcommittee. 24, Working Group 8. You can read about this and go look up those sites. The model is Working Draft of 18026, and you can go to your heart's content and see what people are doing in that area. A little bit about the standard. We define scope, normative references, and remember I mentioned that terms, symbols, and abbreviations. We're trying to settle on a unique and meaningful set, and that's very, very hard to do. There's a concepts clause 4, which when it comes out, you ought to read because it puts everything in context. We define what coordinate systems really are, what are reference data, and object reference models, and that's roughly speaking models of planets and Earths and spacecraft and whatever. We have to tie down time because, as you all know, things change in time. Greenwich doesn't even stay in one place. So there are all kinds of different kinds of time. We pick one, we set an epoch from which we're going to reference everything. Spatial reference frames are discussed in this class and in great detail in this document. Operations on spatial reference frame. Quality assurance, so that how do you know that you built a quality product? There's an application programmer interface, a conformance clause, so somebody can determine whether you're in compliance with this standard. And then there's a process called registration, which allows you to bring new reference models in. Should somebody invent a new Earth reference model, you can have it registered and made part of the spec. What do they call that other one that goes the other way? Deprecation. Deprecation? That's where you want to remove something. Nobody wants it anymore. So they have formal processes for this. There are several annexes, some of which are normative. That means they're binding. There's an annex on relation to other activities and other standards activities. There's a rather neat one. We've removed all the heavy-duty mathematical concepts and put them in one place so that people that have an interest in that can read them in one place without overly complicating the standard. And Paul wrote most of that. There's a bibliography, rather extensive but not binding. And then a whole list of official registered surfaces, parameters, models, and whatever. And now we have Paul, who's going to talk about the next section.
Good morning. So how we get there? Well, we're going to talk a little bit about coordinate systems in an informal way, but in the spec, we try to do it in a very precise way. And as Ralph mentioned, there's a lot of disagreement as to terminology. This is a sufficiently old subject that there's a lot of history behind it, and people use terms to mean similar but different things from each other. So one of our objectives is to give a very clear and unambiguous definitions of the terms we use in a way that's self-contained in the standard. And we also deal with types of coordinate systems because various categories of coordinate systems create problems that are similar and dealt with in a similar way. Reference datums are the parts that we use for reference datum sets and RDS classes, and we'll see in a little while why we need these things. Ralph has already mentioned that we need to be very clear and unambiguous about what we mean by time. And then we need to create object reference models for the objects we want special referencing for. And then we put these parts together and produce spatial reference frames for which we can look at operations. And when we put all this together, the conglomeration of all this is going to be the spatial reference model, the SRM. This is an intuitive slide of some coordinate systems that you've seen in high school algebra. We have a line, and we pick 2 points. One is an origin, and we pick some other point that's going to represent one unit, and that's going to then determine positions on every point in that line with a single number, and that's going to be a one-dimensional coordinate system. Similarly, we have two-dimensional and three-dimensional. Once we get to three-dimensionals, there's left-handed and right-handed coordinate systems. All rectilinear coordinate systems in the SRM are right-handed, so you might notice that this one wouldn't be allowed.
Except for that picture.
That's a left-handed one.
Which we copied out of the current version.
Just as an example, different places in the literature, rectilinear means one thing one place and something else somewhere else. Similarly for Cartesian. basically, if we have a vector-based structure in our coordinate system, we're going to call it rectilinear. And a Cartesian coordinate system is a rectilinear one whose basis vectors are all of unit length. So over here, we have a Cartesian one because we see the distance to the unit point is the same in both axes. Whereas over here, the distance to the unit point is short, and there it's long, so that would be non-Cartesian. And then there are oblique axis coordinate systems in each of these kinds, which create all kinds of distortion, so we want to be able to identify and talk about these things. And that's just the beginning of the kind of terminology we need to deal with.
I have a question.
Yes.
One thing I noticed about when you talk about coordinate systems and what they've been in the past in distributed exercises, they basically work in a Cartesian reference frame. And you have polar and you have spherical. But, I guess because your theater is so the play box is confined to a certain area, you don't have to worry about transformation and doing a different coordinate system.
Okay. The question, if I can summarize it, was that in some situations the playing field, the sandbox you're playing in, is relatively small, and you have one coordinate system that you've picked, and so you really don't have to worry about transformations and things of that sort. Well, that's true as far as locating things, but once you want to do things like dynamics, then already you need to begin to worry about just exactly what your spatial reference frame is, and we'll see a little bit of that later on.
We are going to address that subject in more detail later on.
So here come curvilinear coordinates. You have a tuple of numbers, mu and r, and that gives us a place on the plane. Cylindrical, get mu r and a height z, and that gives us a place in three-dimensional space. And here's a spherical coordinate system. Again, 3 parameters giving us places in space. Curved coordinate system, that's one that maps a domain in R1, the coordinates, to a smooth curve in space. A surface coordinate system maps a domain in R2, so these are 2 tuples of numbers onto a smooth surface. So, for example, this is geodetic, or more generally, we're going to call it celestial detic coordinates, in which here's a point on the surface of this oblate spheroid, and we measure angles according to some reference datums, and we end up with a pair of numbers. So these pairs of numbers are the domain in R2, and there's one pair and only one pair for each point on the sphere. We can extend some curved coordinate systems to 3 dimensions. Here we tape perpendicular to the surface, and that gives us a line, and we can measure up and down on that line, giving us a 3rd coordinate, and then we have a 3-dimensional curvilinear coordinate system. A map projection is a surface coordinate system that's defined by a smooth one-to-one function that associates a subset of points on an oblate spheroid, or a special case sphere, with a set of points called the range of the projection. One-to-one is important because, again, any coordinate has to identify exactly one place, and any one place in the domain has to have exactly one coordinate set. The function that takes tuples of numbers to places on the plane is called the generating function. Map projections generally do not convert the entire surface. Some regions of the surface and certain exceptional points, such as poles, may not be converted, and the range of the generating projection may be a proper subset of R2. That's because, we'll see in some examples, the way the projections are made, you can't get everything on the spheroid, But even if you could, sometimes you restrict the domain for distortions reasons, and we'll talk about that a little later on. The map projections that we treat in the spatial reference model are Mercator, oblique Mercator, special case of that, transverse Mercator, Lambert conformal conic, which I think the atmospheric community likes a lot, polar stereographic, and equidistant cylindrical. How do we do spatial referencing? Well, we talked a little bit about coordinate systems, and what really we've done is we've talked how coordinate tuples essentially give us unique addresses for points in Rn, where n is one-dimensional, two-dimensional, three-dimensional. So really, we're talking about coordinate systems for Euclidean 3-space, for example. What does this have to do with the real world that we really want to reference? So our goal is to associate these coordinate tuples with positions in the space of an object. For example, points in this room, real places in space. Well, one way to get there is to embed Rn into the space we're interested in. Then points in Rn will be associated with positions in space. So one simple way of doing an embedding is pick an origin, some particular point in this room, for example, and then pick perpendicular directions and unit vectors in each one, and we can set up a coordinate system that essentially embeds R3 into this room, and then we can pick a coordinate system which will give us, say, 3 tuples of numbers that will uniquely identify every point in space in this room. So that sounds simple enough, I hope. But there's a problem. Simple embedding methods not always possible. For example, in the geocentric system, the origin is somewhere in the center of the Earth, and so you can't point to it and say, that's the origin, that's the spot. So that makes it hard to do a simple embedding. Well, geodesists have been doing this for a long time, and they use an indirect embedding method. And to build up to that, we have this terminology of reference datums. These are simple geometric constructs. And we put some of them together in specific reference datum sets in a way that the geometric relationships between these geometric constructs can be used to unambiguously create an embedding of Rn into space. And then we have an object reference model. That's a geometric model of an object together with a reference datum set that has a measurable binding of the model to the space of the object, something that you really can put your finger on. And then a binding of the reference datum set to that object reference model. And between those two bindings, we'll get an embedding from Rn into the space of the object. Now, let me try to make that a little bit more concrete with an example. We're going to create, or at least give you a recipe for creating the Vancouver 2002 object reference model. And it's going to be a model of the Earth, and that actually has a special case. It's called the ERM. Instead of an object reference model, it's an Earth reference model. But this is a generalized recipe, so I'll just keep ORM here. Okay, the model of the Earth is going to be a sphere reference datum with this radius. And we want to bind that model into space. And so in this recipe, we're going to pick a spot on the ground in Vancouver. And when you registered, you all got this map, and you'll find on here clearly marked the location of the Gastown steam clock. So we're going to take the middle front base of the Gastown steam clock, and that is our spot, the Vancouver spot. And then we're going to measure the direction of up at the spot. and that's going to be called the Vancouver normal. Now, what is up? That actually is something that the SRM doesn't care about. Geodesists care a lot about. We just care that there is some direction that's been picked. You might want to hang a plumb bob at the Gastown clock and take that direction as up, or you might want to have 20 plumb bobs somewhere around Greater Vancouver and average them. There's lots of ways you could define up. And then we want to measure the elevation of the star Polaris with respect to our notion of up. And that's going to determine the latitude of the Vancouver spot on this sphere. And that gives us our measurable binding, because there's one and only one sphere in space that satisfies these four conditions. It has this radius, its axis intercepts Polaris, the Vancouver spot is on its surface at this latitude, and the surface normal at the Vancouver spot corresponds, the surface normal lines up with the Vancouver normal, and that gives us a binding in space. Now, for our ORM reference datum set, we're going to take these four reference datum geometric concepts. We're going to have a line representing the y-axis, a plane representing UV, a plane representing RD, representing the UI plane, and a point representing the origin. We're using UV and W instead of XYZ because XYZ belongs to the coordinate system, and when we do the embedding, then embedding identifies UV, W directions to XYZ directions. So that's our reference datum set, and we have to bind it to our model. So we'll take the y-axis and make it the same as the axis of the sphere that was pointing towards Polaris, and bind the UV plane to the equator of the sphere, bind the UW plane to the plane that contains the sphere axis and passes through our Vancouver spot. And then the origin will be the intersection of the axis with the UV plane. And now, given that, we have to be sure to record the epoch of the binding, because however we measure it up may change in time, and similarly for the elevation of Polaris and other such things. And this ORM implies an embedding of R3, where we make these identifications. And so now there are many coordinate systems we can now bind to this ORM, or ERM. So we could put a surface coordinate system on the sphere. We could put a 3D coordinate system in various ways, and we can use map projections on a portion of the sphere. Augmented map projections built on those. We'll talk about those a bit later. So here's a picture of what we've got. Here's our sphere, and here's this normal to the sphere, and corresponds to the Vancouver normal, and this elevation angle points to Polaris and at the Vancouver spot. You notice that this model looks like it's pretty good around Vancouver, but I don't know about the rest of the Earth. Models like this are sometimes called local datums. Local datums because they're good in the area that they were designed for, but not necessarily good globally. Historically, almost all datums were local datums because that's the best that could be done. Around the 1970s, satellite telemetry advanced to the stage that people could really get a good idea of what the shape of the Earth really is, and then try to get models, position oblate spheroids in such a way that it was a reasonable match globally. And then we begin to get global datums. But most of the maps, a lot of historical data is built on the local datum, so we have to be able to transform between those and global ERMs. And in fact, in the SRM standard, we list scores of local datums and the parameters that you would need to transform between those and global reference models. So how do we get a spatial reference frame? Essentially, we take an ORM and we bind it to a coordinate system, and the result is a spatial reference frame. It's convenient to deal sometimes with sets of spatial reference frames. For example, UTM has a set of 60 zones, and we can treat them in a uniform way, and we put them into a spatial reference set. Okay, we've been talking about reference datums as simple geometric constructs. Part of this of the specification, we try to unambiguously define exactly what these are. We've already used a point one in our Vancouver ERM, and we have formula for a line. Specification of a circle. This is implicitly generated by this function. Essentially, all pairs of u and v for which this is equal to 0 give us a circle of radius r. Look at all UV pairs where v is positive, and we'll get a hemicircle. The 0 set for this gives us an ellipse with major and minor axes A1 and A2. And we can get a hemi-ellipse. This is a sphere. Look at all UV, W tuples that set this expression to 0, and it'll be on the surface of a sphere of radius r. And we have the oblate spheroid. We'll be using OBS through much of this presentation to mean oblate spheroid. And if we change minor and major axes, we get the prolate spheroid. And we can also deal with the plane. We've dealt with, we had 2 planes in the Vancouver 2002 ERM. So reference datum set, which we saw an example of, is a set of one or more reference datums and relationship specifications that's going to facilitate the embedding of a coordinate system. And we have RDS classes, which are essentially sets that are parameterized. And we have RDS classes, which includes a unique name, a set of parameterized RD definitions, giving us the members of the RDS, and the relationships that we can use these over and over again for different objects that we need to model. So here's an example of orthonormal class, which we could use, for example, to embed a celestiocentric coordinate system. This one is built out of 3 planes, but there are other ways you could do it. Oblate spheroid, which we have a plane which is going to be the equatorial plane for the oblate spheroid, and then there's going to be a designated meridian, which, for example, would run through the Vancouver spot if we're using this RDS class in our datum. So we've established concepts of coordinates used to express a location with respect to a coordinate system. We briefly touched on coordinate system types. I've showed you what reference datums are and what role reference datum sets play in object reference models. And these are then, this is what's in the SRM. How you bind them then becomes something which is external to the SRM, but that establishes a spatial reference frame. Which brings us to
Good time to break the film.
Change the tape.
It'll be a short, very short pause.
If it's
30
like,
seconds or so.
And I'm going to say something about SRF sets. You may wonder why they're there. Why don't we call it UTM? Well, one of the SRF sets is GCM, and there are 47,000 of them. We don't want to have 47,000 different spatial reference models, so we collect them into a set. Abstract surfaces geometrically. If you think about it a minute, it's easy to find a circle, but hard to define certain geometric surfaces that are more complicated unless you write down a mathematical equation. So I'm going to talk a little bit about map projections, augmented map projections, and geometric distortions. And down at the bottom, well, first of all, map projections have been around a long time. You don't want to take anything I'm saying as a criticism of the art of making maps. People need maps. That's the pieces of paper that you do planning on. But that doesn't mean that you should use map projections as coordinate frameworks to do simulations with. That's the distinction. And the gentleman who asked the question has left the room temporarily, but this is part of the answer to his question. Projections and augmentations to the projections are used and used and used, but are distorted and distorted and distorted. And why do they get distorted? Well, there are some surfaces you can develop. Term means that if I take a cone and I cut it with a pair of scissors, I can flatten it out. And nothing tears. No stretching. I can take a cylinder and cut it, roll it out. No tearing, no stretching. But when I get to a sphere, I might try to do it like the blue figure on the left, but that's kind of inconvenient to use. It's really torn. If I take this orange here and try to squash it out into the plane, it stretches and tears. That's the effect of the distortion. You can't cut it and make it flat without doing this damage. So projections are a way out of this problem. So what's a projection? I'm going to give you projection 101. This is a geometric projection and in the terms of projective geometry. We have a circle. We have a point called N. We're going to have a bunch of equally spaced points. Those are the green or blue points. I guess they're green. I don't know, some color. On the surface or on the circle, I'm going to draw a line through those green points that are on the circle and project them onto a line. Simple geometric construction. Notice there's just one point that I'm projecting from. Some projections have multiple points you project from, and some projections have equations of this moving point that moves around. So it gets very, very complicated, especially in 3 dimensions. But the point I'm trying to make here is that the lengths, which were all of length S, equal arc lengths, get changed in the projected space in the line. They get stretched. Okay, so that's a distortion. There's a distortion of length. Another very important point and he's still not here, is that the red points don't map. It's only the points on the figure that you're projecting. So when we generalize this to the Earth and an ellipsoid, it's only the points on the surface that get projected, not points above or below. Now, the stretching can be somewhat mitigated if I take the green line and move it up into the object a little bit and intercept the green line as shown in the second line down here. The distortion is mitigated by making the scale 1 inside the region, so that here the scale is too small and here the scale is too big. But it isn't as bad as here. We've kind of smeared the distortion over the interval, if you like. This is a common practice in making maps. And here are some pictures of projections of that type. These are cylindrical map projections. This says nothing about how the projection is done. These vertical lines that are on the blue are only there to show you the front of the figure. We don't show any latitude or longitude projections or any of that sort of thing here. But you can have a cylinder that's tangent and whose center is parallel to the axis of the sphere or ellipsoid that's inside. And over here we show that it's cut into the surface a little bit to mitigate the distortion. Planar projections are the same kind of thing. The plane can be tangent or cut into the surface. Stereographic projections are where you set a plane on top. You can embed it, you can put it on the side, you can do all kinds of things with it. This one is a polar aspect. You see what its picture looks like over here. With conic map projections, they can be sitting tangent to the object, or they can cut into the object, and you can cut them along a line and roll them out flat. There's no distortion. Here's the Mercator map projection. We show a plot here of what the world would look like if you just plotted raw latitudes and longitudes. Remember, the points are on the surface, so height is not involved. And if we just blindly plot latitude and longitude as if it were in a rectangular system, you get the upper right picture. Of course, the top of the thing is really stretched, because there's only one point up there, and I had to map it to infinity to get all that. Notice the distortions. And over here is the Mercator projection, which is quite a popular projection for people who live in this region for maps. It's become a political issue in recent years for a couple of reasons. It makes third world countries look smaller than they really are. The further north you are, the bigger you are. If you don't believe that, go look on a globe sometime and notice that all of Greenland fits into Brazil very nicely with lots of room to spare. That's the area distortion that you get from the map projection. So map projections will distort things. You can have cylinders that are at an angle called oblique Mercator. They can lie on their side and they're called and be tangent around the equator, and they're called transverse Mercator. And perhaps one of the most confusing things for people when they encounter map projections, and I really wish I had this animated, we got to fix this next time. But the picture underneath, the gray picture that I took out of that book, is the transverse Mercator spatial reference frame. Shows the picture of where the meridians go and where the parallels of latitude go, but the actual coordinate system, the projection-based coordinate system, is rectangular. It's the red lines. And the origin's right there. And north is that way. And grid north is along these vertical lines. So the actual coordinate system you're using is rectangular. He's back. I can now talk about rectangular coordinate system. This is one way that you can change a curvilinear coordinate system into a rectangular coordinate system. And later on, I'm going to tell you the consequences of that and how bad they are. But this is one of the ways you could do that. And of course, as you get away from the origin, there was more and more distortion. So for military purposes, people have cut the world up into zones, 60 of them, taken transverse Mercator and restricted it to a zone, long, thin region, where the distortion is now minimized, and so that you use this section when you're in a certain region. I don't know which zone that is, zone 14, and if you're over a little bit in zone 15, use the zone 15, and you minimize the distortion. Looks great, used for most ground military maps. There's an obvious problem that occurs though. What if you operate across boundaries? Well, these things are not continuous. The X on one side is not the same as the X on the other side. There's a hop. There's all kinds of problems with that. It's good for mapping because you need it to make paper maps. Where the problem comes is using this as a coordinate framework for simulation because you have these discontinuities all the time. This particular chart just shows that Mercator is very useful for navigation for people that sail ships, because you want to go from Florida to France, you can fly at a constant heading in a Mercator map, which is easy to draw on the map. You use a ruler. Is it the shortest distance path? No. What kind of path is it? Well, it's a loxodrome or a spiral. If you could keep going on it, you'd spiral into the North Pole. But it's good for navigation purposes. If you wanted to save fuel in an airplane, you might not want to fly that path because it's too long. Here's another idea of the effect of distortion. If you plot a great circle arc, which is a minimum distance path on a sphere, between Washington and Moscow, that's what it looks like in a Mercator projection in the upper half. But by rotating the cylinder a little bit and making this an oblique Mercator, you can make that a straight line. Either one of them real? Nope. They're different views for different purposes. And they're great for mapping, but lousy for simulation. Not that I'm biased about that. Now comes a fundamental problem in the modeling and simulation business that addresses this whole business of rectangular coordinates. We're going to keep coming back, and coming back to that. Simulations require 3 dimensions. I just got done telling you the projections are 2-dimensional. So how do you get the 3rd dimension on there? Well, they take the projected point, take the height, geodetic height sometimes, off the ellipsoidal surface and simply move it over there and stick it on. That's called an augmentation. Unfortunately, NEMA puts out DTED data in lat, lon, and orthometric height, which is a different kind of height. Doesn't bother a lot of the modelers. They still grab it, put it over here. Now they've got not only a distortion, they've got the wrong height. And they build a coordinate system out of that, in which they try to invoke F equals ma. At this point, you're dealing with nonsense. You're dealing with nonsense geometrically also when you try to do line of sight. We'll be saying some more about that. So there's a common to augment the vertical axis of the projection, putting a vertical axis on there. Now, everything would be pretty good if those vertical axes were all in meters. But people like Lou Embry come along and they want pressure altitude. Not even in the same units. Not a Euclidean space, and it's not an orthonormal system. Now, usually when we give this lecture, there are people saying, well, wait a minute. Cartesian means orthogonal. No, it doesn't. Cartesian means the unit vectors are the same. It has nothing to do with orthogonality. There's orthogonality, and there's the metric being the same on both axes. And Paul gave you examples of rectangular systems, orthogonal systems, that are both Cartesian and non-Cartesian. And he gave you examples of oblique systems that are Cartesian and non-Cartesian. These augmentations are very often orthogonal but not Cartesian because the units are different. How can you have a Euclidean distance? Think about it a minute. Okay. And this practice of putting augmentations on makes the distortion much worse. Here's the set of conversions that we use in the SRM, and we've shown. I keep pointing at this now. If we have a spherical OBS, you can do map projections off of it and get different map projections off the sphere. And then the notation over here says, oh, by the way, you can make these three-dimensional if you want by augmenting them. So those are the things that we actually consider. Now, we had a little problem in trying to sort out. You heard me use the word real-world coordinate system. Well, what does that mean? Doesn't mean anything. They're trying to sort out what does it mean to say that some of these transformations or conversions rather are no good, that they distort. And trying to put a taxonomy together that puts us in two classes, those that distort and those that don't distort. Well, if you go look in math books, you'll find all kinds of stuff like isometric, linear, bilinear, just tons of names of things that represent mathematical transformation. Too much for us. So we came up with this idea. There are really two classes of conversions that we want to deal with. Those between spatial reference frames that do not distort geometry. Now, what's an example? Well, geodetic coordinates, lat long, convert that to geocentric coordinates. Does that distort anything? No. The points stay where they're supposed to stay in inertial space. Those do not distort any geometry. What are geometry distorting operations? Well, I just gave you some. Projections all distort geometry. And if you add a third axis, makes it worse. So those are in the class of geometry distorting operations. And as you could well imagine, it isn't just stretching and misplacing, but angles aren't right anymore. Azimuth doesn't mean azimuth anymore. Elevation doesn't mean elevation. And distance doesn't mean distance anymore. And so we recategorize the set of conversions that we have off the oblate spheroid. And we always, of course, use green for the good ones and red for the bad ones. Yeah, Kevin?
Well, since projection-based systems, and particularly augmented projection-based systems, have these problems, why does the SRM support them?
Well, because we have to support.
Repeat the question.
Oh, I'm sorry. Kevin said because projections and augmented projections have problems in terms of distortions and the things I talked about, why do we address them in the SRM? Well, the SRM is broadly based. It can apply to geodesy where they still make maps. And so we need map projections. I'm not here to tell the user how to use these things. I'm here to tell the user what the consequences of using them. When I said they distort and that's bad, I meant for certain applications, modeling and simulation, embedded system. That's a good question.
Well, it's Stu's intentionally leading question. They're in there because people use them.
Yeah, there's an enormous legacy that we're addressing here. You notice our set of projections is relatively small compared to what Geotrans has and what the oil company has and so on. And that's because we're trying to get away from all of those strange projections. Good question. I mentioned that it isn't just position that gets messed up, but distance gets messed up, azimuth gets messed up. And then when you add the vertical axis line, you know, we use the word conformal to talk about maps, projections that preserve angles. That's angles in the plane or angles on the surface that they're talking about. Projections only are two-dimensional. It has nothing to do with elevation angle. So if you go and augment one of these projected systems with the vertical axis and expect the angles this way to have anything to do with reality, you're sadly mistaken. They're completely wrong, really. And I'm going to give you an example of that. If your eye goes to the right first, looking at an Earth model surface, looks like a piece of an oblate spheroid, and you have 2 points, P and Q, and you draw the perpendicular so that the points Q prime and P prime can be thought of as in geodetic coordinates, or at some lat long and a perpendicular height called geodetic height. After you map them over to the left onto the map projection surface, they look like this. Well, over on the right, they weren't parallel. All of a sudden, they're parallel. If you're on the left and you're going with the inverse transformation, conversion rather, lines that were parallel in the augmented projection space are not parallel over in the non-distorting space. By the way, this is a geometrically distorting space, and this is a geometrically preserving space. And so distances are messed up, directions are wrong. I have a more complicated chart that shows us again, that's really pertinent to how the Army models a lot of their models using UTM. Somebody asked about surface coordinate systems generally being rectangular. This is one way that people make local rectangular coordinate systems, and they don't know what damage they're doing to themselves. This example shows, it's very similar to the previous chart. There is an observer right here, 6 feet high. There is something they want to observe that's also 6 feet high. And there's a tree in the middle. And the tree is high enough so that the observer cannot see the target. But since I wanted a rectangular system, I transformed all of this to universal transverse Mercator, or just transverse Mercator. And what do? The bottom points map to there. This bottom point maps to there. And I stick the heights on. Guess what? Now the observer can see the target. So if I had 2 simulations hooked together, and one of them was using geodetic coordinates and the other one was using UTM coordinates, I could see you and you couldn't see me. That's called an unlevel playing field. Aside from the fact it's wrong. I have a little model that demonstrates such a transformation. Here is the situation, the tree in the middle, 2 observers, and I'm going to make the line of sight out of this, if it doesn't break again. And here's the initial situation. I cannot see, right? So I'm going to instantly transform to UTM coordinates, and I can see. That's bad. You want to be very careful about using UTM, and why UTM is losing favor with almost all agencies. It is another reason why the modeling community is going to GCS, which is local surface coordinates, 47,000 of them, pasted on the surface of the sphere or on the ellipsoid. That solves some problems, but it creates a lot more problems. Okay. Here's a few observations. This is kind of for modelers so that you understand. This is not about SRMs and stuff, just something about modelers understanding. Okay. How do you put a solid cube on top of a oblate spheroid? Well, it can only touch at one point. So that's the way it goes on. Remember, this is abstraction. There's no terrain. There's no environment. There's just this abstract mathematical concept with a cube trying to sit on it. If you actually do a transformation, and this is common in the modeling business, somebody constructs a building or cube in some augmented projection space, and here's the bottom of that cube, and they map it over into geodetic coordinates because the DIS protocol requires that, and somebody uses it over there. What does the bottom do? Well, the bottom's on the surface now because it was in the plane here, but is it still a rectangle? Is it still a unit something? No, not even convex anymore. The sides are curved. The interior angles are all 90 degrees because it's a conformal map, but the shape has changed. What about the top? This was all 90-degree angles. It gets warped over here too, but now not even the angles are preserved because this isn't on the surface. So conformality doesn't have any meaning anymore. So all of the sides get warped. So things that were nice and convex become warped. You stick them together, there are holes in them. Things that were inside are now outside, and all kinds of interesting problems can occur. Well, does it make a difference? How do you put buildings on a terrain surface? Different problem. These might not be very acceptable, are all cases that I found in databases that the Army uses. Until we had to see it, we didn't even know that these things occurred. With see it, we can see these things. You might want to excavate a little place to put the buildings in, do something like this. One of the points of this chart is the SRM does not address this problem. You have to address it as a modeler. We'll tell you what happens if you do transformations, but you have to do the excavation. We can't do that. We don't even know anything about terrain models. Same thing happens with roadways and runways, causeways. In one world, they're nice rectangles. When you put them on the surface of the OBS, they become curved arcs and they get warped. So augmented projection-based coordinate systems can be and often are, not always, but often are orthonormal systems. Conventional orthonormal systems have a vector space associated with them. You can cross products, dot products, do wonderful things. But how do you get those vectors over to a curvilinear space? Curvilinear spaces don't support linear vector spaces. You move individual vectors, but what do you do about that? We need a method for handling that. Why do we need that? Because we have light sources and all kinds of vector-like things that exist in the real world that we have to represent at more than one surface. And Paul's going to take this section on, but is this a good time for a break, or is it too soon?
It's about 6 minutes till break time.
Can you make it in 6 minutes?
No, I'll try.
What we want to do is, for a point on a surface, we want to be able to associate a good orthonormal coordinate system. And we start with the notion of a surface vector, which is well defined for smooth surfaces, which is the only kinds we deal with. What you can do is, once you have that normal, look at the plane, all points that are on a plane perpendicular to that normal, and go through the point on the surface. And then you've got to have some way of identifying the direction of x, and then you pick y to make a right-handed orthonormal system. And now we have we call a local tangent plane, a nice linear coordinate system defined on the surface of the sphere. These are the kinds of things that the GCS uses. It's also, for example, if you take a plane on the surface of the Earth, and as you move away, the plane is going to lift off the surface of the Earth. If you move away about 1 kilometer, I think it only lifts off about 1 millimeter or something.
No, it's half a meter.
Half a meter. So, for example, building engineers are building a building that are not that big will use this. Basically, they're using this linear coordinate system on Earth. But if you're building something bigger, like Verrazano Narrows Bridge, the supporting towers are visibly not parallel because of the curvature of the Earth. So this has its limits. In any case, we can define a local tangent plane coordinate system for any point on the surface, and if we pick x direction in a standard way, we get what we call a canonical local tangent plane. So here's a picture in which what we do is to specify the direction of y, we measure the azimuth with respect to north, and that parameter and the point position then totally defines this spatial reference frame. And if we make that azimuth angle 0, then that's the special case of a canonical LTP. And this is the space in which we define directions. So if you're on the surface of the Earth, and you want to define a direction you have to give us a reference location. And with respect to that location, we'll build a canonical local tangent plane and then measure directions in that linear space. So that's what we use for directions. In the SEDRIS data model, we have a class called reference vector, and a reference vector has to have associated with it a location component, and that location component is used to build the canonical LTP. They're used to specify directions, and I guess I just said this. That's our definition of how to define what a direction is. No matter what your coordinate system is, we can always plant a canonical LTP and do our calculations based on those directions. Calculations we have to support, for example, is how are you going to relate a true direction in space to a corresponding direction vector in an augmented coordinate system? Or if you have two local tangent planes, different places on the Earth, and you have a direction in one, how can you express that direction, that same direction, in the other local tangent plane? Those are some of the things we have to worry about. We also have to worry about computing that angle of which way is north. Remember, the y-axis is pointing north in the canonical LTP, and you're in, say, a map projection in which grid north is not necessarily north. Well, the difference between grid north is called the convergence of the meridian. You saw this picture for transverse Mercator, in which if you're at this spot, grid north goes that way, but true north is tangent to this curve here, so it's going that way. And that angle is gamma, is called the convergence of the meridian. And it changes by point. So as you're going from west to east, for example, the gammas may be changing. Move up and down, the gammas may be changing. So we need to compute that for all our coordinate systems. In the case of Mercator, it's very easy because all Mercator grid norths point true north. So that's an easy one. But for transverse Mercator, it becomes quite complicated. I think that's the time for the break.
What time do we restart? There's some words in here that need to be fixed up. The word model is used a lot here to mean different things. This is yet another meeting. We've discussed the notion of ORMs, and we're now going to use ORMs not for spatial referencing, but to build physical models around. Terms like geoid, equipotential surfaces, and things like that. They're really part of the environment. So ORMs are useful for purposes other than just spatial referencing. You all know what an equipotential surface is. It's a surface in a force field of constant field potential. One such thing is a gravity equipotential surface, which leads to the concept of a geoid. A geoid is not a geode. A geode is a rock that you cut in half and it's pretty inside. I just reviewed some Air Force documentation in which they consistently called a geoid a geode. And so I had to go and make my smarmy remark in front of them. They're fixing that. And they really meant ellipsoid to start with. They didn't mean geoid. And by the way, this is not just to pick on them, but it shows the misuse of the language. And somebody who really knows gets confused when they read this. What are they talking about? Pressure equipotential surfaces are used by various people. Topographic surface, we haven't talked about the terrain. That's not part of a spatial reference model. Now, people use the terrain as a spatial reference model, like how high altitude above the terrain or something, but that would make a very good coordinate framework. So what we've decided to do is to separate such concepts, such physical models, from our spatial reference models. They're not the same, but you can get between one and the other. Now, what's a geoid? Well, it takes a little explanation here. Start out with the Earth. There's the topographic surface, that's the land masses, including the bathymetry, which is under the water. There's some water and there's some gas. The geoid surface excludes the topographic surface and generally corresponds to mean sea level. Now that's a tough thing to say because what is mean sea level? Well, mean sea level is a statistical measure taken at some point on the ground. You know, somebody actually measures mean sea level at a point. It's a local measurement. And then there's a use of that term in terms of kind of a global concept of mean sea level. What does that mean? Well, that would be something where the seas would go if you could remove the land masses but keep their gravity, like dig some kind of channels through the mountains and so on and let the sea kind of settle down. But it's still a statistic. It's still a random variable. Mean value means average. The geoid is some measure of a constant equipotential surface in gravity that roughly conform to mean sea level. They're almost the same, and then many people just refer to mean sea level and the geoid as being the same. This is an important concept to have. The program I'm involved with right now involves shooting Polaris missiles underwater. You better know where the sea level is, not where geodetic height is. If you're building simulations and you get them mixed up, you might dump Marines into 20 feet of water because the ellipsoid lies above the geoid sometimes. Here's the terminology for this. There's a topographic surface. One kind of Earth model is the geoid. And we have an OBS, oblate spheroid reference datum, which is really an ellipsoid of revolution. It's a nice, smooth mathematical surface. The geoid is also a nice, smooth mathematical surface, but it's lumpy. It undulates. It's like somebody took an ellipsoid and a ball peen hammer and beat on it. It's also not rotationally symmetric. So they're different, but they're fairly close to one another. And their difference is called a separation. I guess I just shot myself. N. And we approximate that separation. Oh, the big H. Big H is the perpendicular distance from the geoid to some point. The point here happens to be on the surface, but it could be up here. So the perpendicular distance from the geoid to some point is called orthometric height. The distance perpendicular to the same point from the ellipsoid is called geodetic height, and they're slightly different, but near the surface they're almost the same. So we don't treat them as vectors, we just subtract them to get an approximation to the separation of the geoid. The geoid is a gravity exponential surface. And what we're trying to say here is we're separating models of physical phenomena like equipotential height, gravity, and that sort of thing from our concept of object reference models as part of a spatial reference model. One would not want to do spatial referencing of the geoid. Why? Well, because it undulates. You could have 2 points that are perpendicular that go through one point. You'd have a non-uniqueness problem. Even though geoids are used by astronomers to set up something called astronomical coordinates, but mostly just to get the vertical at a point, like Paul's example. Getting the vertical at a point has to do with plumb bob directions off the geoid. Don't get them mixed up. You can, in a real planning, you could dump people in water that you thought wasn't there. And it's one of the big problems with modeling using augmented coordinate system. People actually took lat ln from the NEMA-DTED data and stuck orthometric height on top of it. That's the wrong height to stick on the top. It's what's on maps. It's what's called elevation on maps generally, but it's the wrong thing to do for spatial referencing. So with that, Paul's gonna take over here.
Turn up the volume for 1 minute.
Okay, now for something a little different. Spatial operations. We've categorized those into operations on coordinates, operations on directions, and operations on locations. On coordinates, there are 3 kinds. There's conversion, transformation, and validation. A conversion is a process of determining the equivalent location of a point in a different spatial reference frame which uses the same ORM, but it uses a different coordinate system. So here, for example, we have one ORM, and we can use celestial detic coordinates to come up with these coordinates for this point. Or we can use celestiocentric coordinates, these XYZ coordinates, to come up with these coordinates for that point. So starting with one triple of coordinates and obtaining the other triple of coordinates is called a conversion. A transformation, we keep the same coordinate system, but we change the ORM. So here we have celestial detic coordinates in the red object model here. And we have one in the black object model over here. They happen to use the same meridian plane, so lambda doesn't change between them, but phi and h do change. So for example, if you had a GPS system based on the global datum, WGS84, and you wanted to convert that to geodetic coordinates for the Vancouver 2002 datum, you would have to do this kind of a transformation. Validation is a function for determining coordinate validity after a coordinate, or even before a coordinate operation. For example, in UTM, Ralph mentioned how you have these 60 zones and you have this reasonable coordinate system within each zone, but when you get to the edge, suddenly your x coordinate takes a big jump when you move to the next zone. And some people are only going to move just a little bit past the edge, so they don't want to change zones. They just want to extend their zone a little bit. So recognizing that that's what people really do, we define for those kinds of SRF systems extended regions where the distortions are not so bad and we can reasonably meet the accuracy of the, that we're trying to achieve for these operations. So we have this notion of exact coordinates defined where they're supposed to be, extended ones where we go beyond the domain but we can still deal with them, and then invalid ones, which ones we don't want to deal with. Determining an equivalent location of a point between two arbitrary SRFs may require both a conversion and a transformation. Operations on directions. We already talked about the need to know in a map projection what map coordinate north is compared to true north, and that was convergence of the meridian. And we also talked about defining vectors in canonical LTPs and different transformations you want to make between those. The SRM is going to define the operations for azimuth and elevation, but they're grayed out because we don't have implementations for those yet. Similarly, point scale for map projections and geodesic distance are defined in the SRM, but geodesic distance is not implemented yet. All right, this is kind of a review of what the spatial reference model is. It's a set of well-defined coordinate systems, reference datums, reference data sets, time coordinate systems, object reference models, SRF classes that combine an ORM and bind it to a coordinate system so that we can get a spatial referencing system, spatial operations, which I just talked about, and spatial relationships, which we'll look at in a moment, to support these operations. And there's an application programmer's interface that give us access to an implementation of these operations. And there are supporting concepts which we'll talk about again. Quality assurance is specifying the quality of a spatial operations requires error determination, in which we have to define what we mean by error. And Ralph has already talked about that. Depends on your context and application domain. Potential sources of error in spatial operations include formulation error and approximation, round off, truncation, and others when you do an implementation. The errors of this nature should not be confused with errors arising from modeling the true shape of a celestial object. That's something we mentioned before, but needs to be emphasized. In the SRM, the spatial, the reference domain sets used to approximate the shape of a celestial object is assumed to be exact. In other words, all our error computations are in relationship to this mathematical construct of the spatial object we're dealing with. So in the case of the Earth, we're not dealing with a topographical surface, we're dealing with an oblate spheroid. How well an oblate spheroid approximates the shape of the Earth is outside the scope. A fundamental discriminator for the level of conformance verification is the numerical difference between a result obtained from mathematical specifications in the SRM and the corresponding result obtained by an implementation of it. This requires a reference implementation so that one can produce a set of data called the reference data test set. For this point, data points obtained from a reference datum set are taken to be exact or true data points. Quantities in the reference data test set are called test points. Each implementation to be tested has provisions for recording the information needed to compare the reference data test set to support conformance testing. This set of output data is called the test data set, and the difference between the data points of a reference test data set and the test data set is referred to as an error. So, for example, the test data set might tell you how to do a transformation from one ORM to another ORM. And at each point it says, this point in the first ORM should map to this other point on the other ORM. Now you put it in your implementation, and you take that first point, and you come up with different coordinates. That difference is the error for that one point, and we have to accumulate it over this test set. It's desirable to have the number of data points to be large and uniformly distributed. We need it to really be dense. because these, the mathematical specifications of these operations are typically very nonlinear. And so strange things happen. And so you could easily miss critical points if you don't use a dense test set. Once you've specified a reference data test set, it's just a matter of grinding away and evaluating all the points. And of course, you have to come up with some metric for combining individual errors. Levels of acceptance. A particular implementation should not be required to meet the standard at the highest level if it's unnecessary complexity for the application. So in other words, there are some applications in which accuracy is the most important thing. In others, applications, speed's most important, and accuracy we're willing to tolerate much looser tolerances. So all those factors are then going to be combined to decide what your error metric is and when you evaluate an implementation for acceptance. This is really a different subject. There's a section in the SRM standard which talks about registration, and it gives a procedure for dealing with, for example, ORMs that are not already there, or maybe even coordinate systems that are not necessarily there. I got a question during the break about, we didn't mention, and I forgot the name of the particular coordinate system that we don't deal with. It's a non-conformal map projection. However, if it can be fit into the registration process, it makes the SRM open-ended. So if there is certainly a need, that could be included. So these are the kinds of concepts that we can register in the SRM. And early on, Tom mentioned that there's also deprecation for removing things that no one's interested in. I don't think that's all that important in the SRM, but at least we have the balance to registration. I had mentioned SRF relationships. This has to do with the way we implement things. For example, if you wanted to do a conversion from celestial detic coordinates to universal transmercator, we don't implement that directly. We implement that as a case of transmercator. Or GCS, if you wanted to convert a GCS coordinates to Lambert conformal conic, they would first be converted to celestial centric, and from celestial centric to geodetic, and then to Lambert conformal. So this shows those kinds of relationships and how these interconversions are implemented. These are floating out there because the local space rectangular is not tied to real space. It's like a CAD model or something of that sort. So it's not spatially specific. So we don't get a direct conversion between them.
Have I mentioned the importance of efficiency? I'm a numerical analyst by training and spent a lot of time building embedded systems like the AWACS tracking system, the B-1 bomber fire control system, and things like that, where all of these issues come up repeatedly: coordinate systems, speed of computation, etc. I serve as a consultant to the services, and recently was looking at a real-time mission planner that goes in the back of the B-1. And they asked me to look at the software because they were having trouble getting GPS coordinates in. And it was the strangest admixture of spherical coordinate systems, geodetic coordinate systems. It was basically a mess. And I would be scared to get on that airplane and use that thing. And I told them so. And they said, thank you, but we prefer it this way. And charged on. This chart you've seen before. Why is accuracy needed? In the real world, I mentioned it's been difficult to measure, and it's getting better. You got to worry about absolute spatial referencing now. We have these new weapon systems like Predator that goes against absolute coordinates. The Air Force is building blind bombers now. You say, hey, fly automatically out to this position and drop a bomb on these coordinates. You better get the coordinates right. There have been a lot of problems with coordinate systems in recent times. Dropping things in the wrong place gets embarrassing. We have a case that I've looked at a little bit of a utilization of Predator where somebody stares at a screen and sees somebody in a turban, big tall guy, decides, that's somebody we want to target, calls up another Predator that's got a weapon on it, launches the weapon against the target. Somebody has formulated this and used orthometric height instead of geodetic height. In Afghanistan, the separation's 30 meters. And so the net effect of this is the weapon goes whizzing over the guy's head, 30 meters high. Two bad things. You missed them, and you're never going to get an opportunity again, ever. So you got to get that right the first time. Besides, you killed a bunch of goats up on the side of the hill, and you're going to get sued. In the real world, I mentioned relative coordinate systems. The real world is really easy. I'll give you an example of what I mean by relative coordinate systems. And those of you who think about live and virtual combinations need to think about these things. Relative coordinate systems are really easy to handle in the real world. If I want to sight my gun in, I set up a paper target with some aim point on it 1,000 meters away. I have a long-range 20-millimeter cannon I use for deer hunting. We shoot end rounds. There's no question about what the miss distance is, right? We march down there with a ruler or something, and we measure the holes on the paper target, presuming you can hit the paper target. And then you measure some error measure of how bad that was, CEP in this case, circular problem. Never worried about what the environment was like or what my position was or the target's position or any of that stuff. A sophisticated target shooter might worry about the temperature and record it, and might worry a little bit about the wind. And if you're hunting deer, you might worry about whether you're shooting uphill or downhill, which is a favorite topic in deer camps of argument about, do you aim low or high? Is it different when you're aiming up and down? My partner's a PhD in physics from Berkeley, and he always says, you always have to aim low. And all the hunters say, you're crazy. I aim high when I'm shooting up and low when I'm shooting down, and there'll be somebody else doing just the opposite. After a little bit of argument, they turn to me and they say, well, you're so smart. What do we do? And I say, cosine theta is an even function. In which case they get mad at me. That means V cosine theta has the same sign, and you always aim low. Because when you sighted the rifle in, you had full gravity. And when you're shooting up, you don't have full gravity. And when you're shooting down, you don't have full gravity. So you better shoot lower. You'll miss the target every time. So understanding how the real world works makes a difference. Now, in the real world, this is easy. But how are we going to simulate this thing? Simulation is a lot harder. We have to select a coordinate system. We'll pick a local tangent plane coordinate system. We have to put the target and the shooter down in that coordinate system. And we probably want to orient the target plane to the line of sight, just to make it simple. We probably want to put in an aiming model for the trembly person who's shooting to find a shoot time. Now the bullet doesn't just appear down at the target. There's a ballistics problem here. You've got to worry about the atmosphere, the temperature, the air density, and a whole bunch of things, and model this spinning object that it goes down track, the wind. And And you probably have to access a geodetic coordinate system to get all this data, because that's what this is stored in. And then, how do you know whether you hit the target or not? There's no target there, so you have to kind of iterate and minimize some miss distance. And finally, you can compute radial miss at a target plane impact. Any errors you make in any of that process affects the result. What I'm saying is here, you need ground truth calculations when you're doing simulation in order to assess errors. And ground truth is hard to get sometimes. Suppose the target you're servicing is not in the real world. This is where I'm shooting over a hill at a target I can't see. Somebody gives you coordinate system, or coordinates of a target. Now, there's a problem here because those can come in augmented UTM. Guy's reading a map, gives you UTM coordinates, and gives you an estimate of elevation right off the map. So you got X, Y, and orthometric height. The fire control computer probably uses geodetic coordinates back at the base. So it's got to do a conversion and do it right. Calculates all that stuff and shoots. It's not a relative coordinate system anymore. It's an absolute coordinate system because it can't see the target. There may be somebody over there observing where the round went in. That's called a forward observer in a multi-shot system. And he may correct the aiming angles, the firing angles. But when I do this, I do use location data, but no precisely measured environmental data. This is real world now. I may make an estimate, it's windy, but see, I don't have to do that very well because I'm going to correct the shot, right? I only have to make a rough estimate. Now try to simulate this guy. Now you got to put the wind in, you got to integrate the ballistic trajectory, you got to do all that stuff. I didn't build a chart on that, but I'm saying that's difficult to do in a simulation and make it right. So in simulations, we're simulating the weapon system mechanization that's on the airplane, tank, whatever you're simulating, and you have to simulate the flight path of the real bullet. Different problems. Air sources. We talked about excluding Earth reference modeling errors. So what's left? Truncation errors due to using a infinite series that's been truncated. Somebody may come along like me and want to throw away one function and replace it with an approximation to make it run faster. That's okay if the error is small, but you got to address what you mean by the error being small. Iteration errors often present because a lot of iterative methods are used in this business. And some people will iterate once, some people will iterate until they get tired, and it makes a difference how many you iterate. Ooh, I hate to mention this next one. Formulation errors are due to the analyst developing the incorrect equations or logic. Or projections. There's a process for putting them in.
We're up again. Carry on.
Ready? Formulation errors, of course, we do make once in a while. Just plain wrote something down wrong. But what is probably more common, and I see it in a lot of software, particularly this real software, the embedded software, they see that things don't operate good near singular points. Very often people have accounted for the singular point exactly, but that's not the problem. The problem is when you're near a singular point, the computations go to pot. So in one range I'm thinking of, they don't dare have anything fly over a pole. They're in big trouble if it does, or get too close. But that is a requirement. Once in a while we have coding errors. One of the nice things about dense test sets is that you find coding errors you weren't looking for. Round-off error I mentioned before is that generally we advocate using double precision arithmetic because the numbers are so big that we're dealing with that if you don't, you lose precision. The Earth radius is about the size of 7 decimal digits of significance. That's about the same as a 32-bit word that is a 23-bit mantissa. So you got to do something special if you're going to use single precision. What is computational error? This seems to for me, this is sort of straightforward stuff, but it bothers a lot of people. I'm going to say if there's an exact true value of a point, meaning that we have the exact coordinates of a point, and a set of an approximate coordinates of a point, then you just subtract them, square them, take the square root, and that's the diameter of an air ball. It says that's how big the error is. One of the problems we have in transformations, though, is some of the tuples in the n-tuple are in terms of angular errors. So the question is, how do you convert angular errors to meters? Well, you use S equals R theta, basically. Generally, most of the transformations have an exact solution in one direction. So we'll take that direction and generate an exact set to transform to an exact set using the exact transformations. Now we have two copies, the exact one and the approximate one, or we have the source and the target set, and they're exact. Then we apply our approximate methods, and we have a way of comparing. Unfortunately, UTM, or TM, this should say, is a problem because there is no exact solution in either direction. Now, a geodesist might correct me, because if you look in the depths of Snyder's book, you'll find out there is an exact solution, but it's in terms of all kinds of integrals that you can't evaluate anyway. So it's really not a practical exact solution. Problem is here is you have a finite series going one way and a finite series coming back. And so it's difficult to get an error analysis for that kind of thing. There are a number of different kinds of techniques that are used, and this whole part of this tutorial is to advertise the bottom method. Analytic solutions seem to be near and dear to theoretical mathematicians' hearts, but are often impractical for use. Sometimes you can't find them. When available, they seem to be always used. That's the orientation to precision, accuracy, and so on. They have great advantages. They provide exact reference values. They're useful for derivation. And they have the Earth reference model or the object reference model parameters embedded in them, so they're good for any object of the type. Disadvantage is they almost always involve lots of transcendental functions. What's a transcendental function? Well, I could tell you, but I think I'll give you examples. Trigonometric functions, inverse trigonometric function. Why are they bad? Because they're really slow to compute. You'd like to avoid them. So these methods, analytic methods, I will almost always inefficient. And they're usually too accurate. This is another issue. They will compute to, umpty decimal places, and you really don't care beyond a millimeter, The Taylor-Maclaurin series, I mentioned one of the problems with them, but their advantages are they're very useful for derivations. You can get theoretical error bounds. Nobody does, but you could. Again, they have the object reference models embedded, parameters embedded. They can be inverted. All power series can be inverted to get inverses. One of the problems is you start deriving these things, and you got to use the chain rule for partial derivatives in more than one dimension. And things expand in complexity until you can't stand it, and you don't know if you've made an error. In fact, you have to use Mathematica or something like that just to get the terms. And probably you're going to have a lot of round-off problems because you got so many terms that you're computing, you're going to lose the solution. Also, the truncation error tends to grow monotonically and rapidly when you get away from the expansion point, and they're not as efficient as other approaches. Iterative methods are sometimes useful, but and are essentially exact solutions. Again, the parameters are embedded. They're always almost more efficient for the same accuracy than power series. And usually the expressions involved are compact, so people really like them because they can code it easy, but they're slow. Conversion rate depends on the formulations. Everything depends on the initial guess. Direct approximations, which I'm about to talk about, are almost always better. And this is a fairly recent phenomenon to make statements like that. When I was just starting in this business, we had to do trade-offs between runtime and memory. Remember that? Well, memory is not a consideration anymore. We have tons of dynamic random access memory. So we can take advantage of that. And what I call a direct approximation of a function or its inverse, you might call table lookup, colloquially. And you might just use linear approximations or quadratic in some cases, or rational functions in some cases. And in a sense, you can embed the parameters inside this because you can do the approximating coefficients at startup time, so they relate only to your Earth reference model. And with modern architectures, this works much better in terms of speed and accuracy than other methods. And so suddenly you use 1,000 kilobytes of RAM to do some function. Who cares? So if you exploit the low-cost dynamic random access memory, one of the things that you can do, you should do, mathematicians, I was trained to always worry about using variable step sizes and stuff. You don't want to do that anymore. That was to save storage. You want to use equally spaced reference data. Why is that? Because you can index them. You divide by a number or take the greatest integer part or fix it or float it, fix it, and you get the index of the particular interval that you're in. It's a little inefficient from a theoretical point of view in terms of memory, but you don't care about memory anymore. So you can quickly find out where you are in a table and use linear approximation. And then if it's not accurate enough, you just make the number of lattice points in your table bigger. Sounds simple, but there's a lot of details involved. One of the things that used to bug me when I first got involved in this business was the lack of dense test sets. You've heard that mentioned 3 or 4 times. Some people would test their code on 50 points and say, I'm done. The problem is 50 points were essentially the same point in a topology sense. And they never tested their singularities, and they didn't do enough dense testing to flush out where the inaccuracies are. And what this chart says, if you're using a Taylor series expansion, which was common at the time, still is, and you happen to pick your test point right at D1, you might conclude you have a heck of an accurate system because you picked a point where the error happens to be 0. But you really need to spread your your errors over the whole region to detect that, oh, they're really bad over here. If you use a dense test set on that x-axis, you'd find that out right away. Checking at a few points can give you bad results. Gets much worse in 3 dimensions. So this again drives home, this chart drives home again the case that you really need to sample uniformly and on a dense set in order to find all the bad points. And in doing so, you will also find coding errors that you didn't even know were there because you didn't sample on a dense enough set. Small errors. Small errors are interesting. A lot of people say, oh, well, that effect is small. Well, small doesn't apply to horseshoes and hand grenades, remember? Small depends on the application. Take comments like, for small regions, all the map projections are the same. That came out of Bowditch. First off, Bowditch is a really old book. And in those days, navigation, if they got within 20 meters, they're great if you're sailing a ship. I had a discussion with somebody at the break about that aviators use Lambert conformal conic as their basic maps. What are aviators interested in? Flying private airplanes. You're looking for waypoints, right? You don't care about being very accurate. You want to just be close enough so you can find something or a beacon that you use to plan your flight with. That's good enough. It's not so good if you're trying to simulate that kind of thing. So it's somewhat dependent on what you do. So in some kinds of navigation, meters of error are small. To some geodesists, meters are big. To others, they're small. Depends on what kind of geodesy they're doing. If they're doing long line surveying, they worry about meters of error. In GPS, a meter error is big these days. To a gunner, I talked about gunners aiming at turret ring. A meter is really big. I talked about and showed you the little model that how many times do you think that you just can't see? Think about that a minute. It's not a point process. It's the accumulated number of times that you can't see when you should have. Suppose there are a lot of those. Certain kinds of terrain, there are a lot of those. Is that going to have an effect? You bet. And in some kinds of systems, small errors may accumulate. The application domain determines what is small, and you really want to keep things fairly good in order to do VVNA. Now here's a funny terminology, which I got from Jerry Linkowski, by the way. Something called fuzzy creep. There was this problem of people were complaining, hey, we got this table of data from NEMA, and we put it in our system, and then we did a round trip on some coordinate conversion, and we're way off. What's the matter with your data? Well, what they've done is they've taken this data, converted it to single precision, did single precision coordinate transformations, and couldn't get back to where they were. They're off by a meter. Not surprising. Wasn't anything wrong with the data. So they invented a term called fuzzy creep, coordinate drift. You got to be a little bit careful with the fact that digital computers have finite word lengths. This is very important too. You know, people say, oh, you don't need to be that accurate, but if you're doing an urban combat model, a building's represented by polygon, and you as a simulation guy who's doing the planning put a person inside the building, that person, that object, that simulated person that's inside the building is depending on that wall to keep from being seen. So you mess up the coordinate system, and a little bit of air puts them on the outside of the wall where he can be seen and killed. So it makes a difference depending on the simulation environment you're doing this for. Coordinate transformations can only be exact in rare cases. There's always some error. Generally, you don't get this creep from iteration. If you do, you better fix it. You just need to be aware of it. A very important point in the last thing. I get calls on occasion. I used to get a lot of them, but I holler at people now. They don't call me so much on this. They say, well, we took a point and we converted it from UTM to geodetic, and then from geodetic to geocentric, and then from geocentric to geodetic, and then back to UTM using your algorithms. And we started out in zone 15 and we're now in zone 16. What's wrong with your algorithm? Well, they picked a point right on the boundary. And the accumulated round-off error, truncation error, put you in the other zone. You got to be aware that that can happen. Now, I know how to fix that and make sure you end up in the right zone, but so far nobody's willing to pay the money to do it. This relates to our extended region and our non-extended region issue. And that has to do with bounds checking. One of the things we have is people putting databases into SEDRIS and finding out the entire database is messed up. And they've spent a lot of time putting it in there and processing the data to find out everybody's in the wrong zone because they made a mistake. Because, you know, I challenge anybody in this room, given a set of XY coordinates in UTM, well, Kevin maybe could do it, but not very many people could say what zone they're in or whether they're valid or not. How do you determine that? Well, you first convert them to geodetic and look at them in terms of lat long, but that's very expensive to do that. You don't want to do that. So we're trying to automate the bounds checking to tell you whether your point is valid, invalid, in an extended region or whatever. But that leads to what are the acceptable bounds? We get into arguments about that. We're going to discuss that in a bit. Distortion occurs not only in length, but also in areas, angles, and shapes, and I mentioned that. Angles for conformal map projections are not distorted in the plane, but you can't control all these simultaneous factors. In the SRM standard, I once wrote, map projections may distort one of these factors. And Charles wrote, always distorts. And what I meant, Charles, was there are a few points that don't get distorted, the ones on the equator. But the point is, you can expect the distortion always when you're using map of something. You can control some things, you just can't control everything. And so there are all kinds of projections used for different purposes. Some people want the shapes to look right. Some people want the distances to be right in a certain region and so on. And our measure of distortion is something called point scale. Take care in reading the literature. A lot of the books address this as point scale doesn't need a lot of high precision. I can use a simple little formula. And you rattle on through pages and pages of text working this out, and you find out he's talking about a spherical reference model, not an ellipsoid. For an ellipsoid, it matters. These things are dependent on latitude and longitude generally. For transverse Mercator, the constant point scale is 0.996. Long, that's the one that's kind of embedding the cylinder so that we mitigate the distortion over the whole region. So a measure of distortion error is the point scale minus, that doesn't look right. The formula doesn't look right. But anyway, we can get a measure of distortion. And so I did a study in which I did the following trade-off. Do I take lots of terms in a series to mitigate the distortion? How many do I take before distortion swamps the accuracy of the computation? Why do I want to not take so many terms in a series? It's a runtime issue. So computational time may be swamped by distortion. So I did an experiment. I used some linear distortion data. I use linear distortion as a measure. I use the representation that I took out of Tech SR7 is a Army publication. It's referenced in the back of this tutorial, so you can go find it. It's a handbook for transformations, coordinate conversions, and other things. There are more exact solutions available in P.D. Thomas, which is shown in the next slide. Point scale is directly related to linear distortion. And what I did is I defined it in terms of meters per kilometer. And so if you're less than 1, it means the line is too short. And if you're bigger than 1, it means the line is too long. This is a dual purpose slide to tell some of you, be careful when you read the literature. I'm going to use these later on, but this also tells you to be careful because authoritative sources sometimes appear to disagree. Snyder says this is the formula. Tech SR7 says this is the formula. They're different in the two red boxes. This box is different from that box, so who's right? I don't know. So we go look at P.D. Thomas, who's got a longer thing in here, and there's the 14. and there's the 58, and a bunch of other stuff, but I can't find those. And it's a complete mystery to me as to why Snyder has those. He must have had a rationale. I don't think it was an error. I'm just warning you that they're different. Does it make a difference? Well, as a consequence of this, the Geotrends guys went to use this one, right, Kevin? Then there's no argument.
We spent a long time trying to resolve the difference between the first two.
But just think all the money you made doing that.
They did at least two different series substitutions, and then they rearranged terms in different ways, and of course they just said it's all left as an exercise for the reader.
This is a, if I could be critical of some parts of the community, they don't do the mathematics very well when they derive these things. They could do error analysis. These could be done so that you could theoretically know how many terms you need. But it does get very complicated. Look at the terms I had up there get worse and worse and worse. If you get the next term, it covers 2 pages in the text. And you don't even know if they're derived right at this point. You need Mathematica to determine that. So what I did is a little experiment. On this axis, I have latitude in degrees, and on this axis I have longitude in degrees, and I use transverse Mercator, and the 1 millimeter, this is the truncation error. There's where the truncation error is 1 millimeter or less in this region. Now 1 millimeter isn't very big, guys, a little bitty thing, right? So that's really good. And there's the 1 centimeter and 1 decimeter, which is 10 centimeters. And you can see, you can go a long ways away from the origin, out quite a few longitude degrees before you need any more terms in the series. In other words, those even the simple formulas are exact, essentially. So maybe we ought to consider throwing out terms rather than, because they're kind of too exact. And I wanted to compare this truncation error to the distortion error, and to do that I needed the point scale formula. There it is. Point scale in this case depends on both longitude and latitude in spite of the often stated they're independent thereof. They really are dependent, especially in a oblate spheroid case. And this still is truncated, but it's pretty accurate. And I used that to get distortion bounds. There's quite a few things on this chart, so I'll go through it slowly. This purple line is the line where the point scale is 1. Remember the 0.996 is to make the point scale 0.996 along this line. That's the blue line. And then the scale is 1 along this line. And you can see the worst case is down here. Up here you're going to be pretty sloppy and be inside here, and the scale's not too bad. But along the equator, which is what this line really represents, you're starting to get, you have a point scale of 1 here, and you're starting to get distortion. So the first distortion boundary that I have is 1 meter per kilometer is this line. Now notice the dashed line, that's 3 degrees bounded by 82.5 or whatever it is up there, are the UTM boundaries. So if you use UTM coordinates, you can expect distortions of about 1 meter along here. The previous chart showed there was no computation error in the series, so all the errors due to distortion. But if you start operating out here, like at the yellow line, the distortion error alone is 5 meters per kilometer. And as you get out further and further, the distortion destroys you. So there are people that come along and they say, well, we need to take more terms in the series, but they're already too accurate. And if you try to operate out here at 12 degrees, the distortion is so big that the numbers are really nonsensical. Why did I do this little study? Well, we have to find these bounds to use in our bounds checker. And we have to do it for every map projection. And it's non-trivial exercise. We're going to do it someday. And so when you pick bounds, whose wishes do you satisfy? We have some users of SEDRIS that want to operate UTM to 6 degrees. And we say, you better not do that, It's your choice, but you better not do that. So we don't let them do that. We let them go to 3.5 degrees and tell them, oh, you're in the extended region. But if you want to go to 6 degrees, you better use transverse Mercator, and you're on your own. So we don't quite know where to pick the validity boundaries. And there is this thought that maybe we ought to have discrete levels of distortion errors. We got enough troubles now, but. And so as we proceed through this SRM development process, we need to get some kind of standard, something like IEEE standards for computing. They specify how many bits you need in a mantissa and the accuracies and that sort of thing. We may have to do that. There's precedence for this kind of bounds checking. If you put a negative number into a square root routine, you'll get an error message, right? That's an equivalent thing. You're in the wrong region. If you get too big a number or too small, you get an overflow notice. Nobody specifies computational performance, but the big computer manufacturers make their library functions as fast as they can because that's market driven. They can sell more of whatever they're selling, computer system. Accuracy, this is the thing, I used to do this for a living, build those things, and accuracy is always specified to the worst case user. So you're always getting way more accuracy than you need 99% of the time, but that's the way the life is, I guess. Most applications never come close to needing full accuracy. No options are provided usually in standards for reduced accuracy, but you could do that. One other thing I mentioned once already is called a chaining problem. If you're going to do a coordinate conversion from celestiocentric to celestiodetic to UTM, or to TM to UTM and back again in a chain, programmers don't like that. They don't like to call 4 pairwise calls. They want one call that goes directly from here to there. So they put together chains like that and then call me up and say there's something wrong with your software because I do this circular thing and I don't get back where I started. So all I'm warning about in here is if you're going to build chains, please let me do it. So that I'll take care of putting things in the right intervals, and I'll also make it a lot more efficient. A lot of these chains, and some of you who do embedded systems will see this all over the place, you go from celestiocentric to geodetic. The process that we use, which is very efficient, automatically gets the sine and cosine of latitude. But the algorithm only produces latitude. So the next guy who uses it to get UTM, what's the first thing they do? They compute sine and cosine again. They just had it, but they threw it away. So if I were designing the chain, I would have kept that, not computed it again. There's a lot of examples like that. So chaining is very important. Okay. And I'm off the hook. Oh, wait a minute. No, I'm not. That's too bad. This is going to answer partially your question back here about why do people use orthonormal coordinate systems, which he called rectangular, but he really meant orthonormal, and he'll say that forever now that he's taken this class. When you derive and develop dynamics equations in rectangular coordinates, the velocity and acceleration components don't contain trigonometric functions. Believe me, I'm not going to go through that. I used to have the equations up here, but people threw things at me from the audience, so I don't do that anymore. Just believe me, they're fairly simple. However, the right-hand sides, the forcing functions that go with those rectangular orthonormal systems, do contain trigonometric functions. There's some nice properties of rectangular systems. Straight lines are linear functions and vice versa, both in time and in space if you're using kinematics. The Euclidean metric only requires a square root. That's an advantage. In other coordinate systems like surface coordinates on an ellipsoid or on a sphere, Minimum distance paths are not easy to compute. What are they? Great circle and geodesics, which don't even have a closed form representation. The Earth and its natural environment are modeled with an Earth reference model and some model of the environment. When you put the environment on top of your Earth model, what's the minimum path between here and Seattle? Minimum time path. Well, you don't have the faintest idea, right? There are lots of possible paths, depending on the weather, time of day, and a whole bunch of things. So when you put the environment on top of the Earth reference model and want to talk about minimum time paths, minimum distance paths, it has less meaning. So don't get great circles and geodesics confused with real-world paths. Talked about Euclidean distance being simple, and you can all read about this. And this is this issue of in the real world, when you put an environment in there, you don't go directly up and over the mountains. You contour around, and there are lots of different paths, and they're not unique. So one has to be careful about the word distance, too. Now, this is really the meat of why people want to use rectangular coordinates, and I've tried to simplify it as much as I can. In inertial coordinates, you get some vector differential equation like this for kinetics equations in which there are no trigonometric terms. But the instant you transform those to geodetic coordinates or any curvilinear system, you're going to get trigonometric terms all over the place in the velocity components and in the acceleration components. And so that's why people like rectangular coordinates. The drawback to the rectangular coordinates is that they're usually wrong in the sense that when they derive the rectangular coordinates, there are no trig functions in the velocity or acceleration, but there are lots of them in the forcing function because gravity doesn't line up with the coordinate system anymore. And you got all these little trig functions. And then what do? You say, oh, well, the angles are small, and I'll throw those terms away. So you get the wrong result. So there's a trade-off here.
Well, that's kind of like the problem where in physics you would calculate, dropping a ball off of a building, and you calculate the time it takes to fall or the height or whatever. Then you got a different situation. Now let's throw the ball off. So you got a different set of components that come in effect. But there's also some things that you can like do away with because of what you're doing. Now
Well,
you throw it. Like I said,
What he just said is this is application dependent
right.
on whether you can do these things or not. And we just wanted to warn you that many applications, many that I'm involved with, like reentry vehicle ballistics, require you to use a proper Earth model, a proper gravity model, and so on. Otherwise, you'll miss big time. Okay, now Paul.
Well, how does this fit in the SEDRIS DRM? In the DRM, we've implemented 26 distinct spatial reference frames and spatial reference sets, either as subclasses of the abstract object location 2D or location 3D. And so you can see the list here. We have local space rectangular, which is typically used for models. Geocentric, 2 and 3D. No, just 3D. Geodetic, 3D and 2D. Local tangent planes, we're talking about GCS, which is what, 47,000 really? It's a set. And then we have projection-based, Mercator, oblique Mercator, transmercator, Lambert conformal, polar stereographic. This is a set. UTMs are sets. We'll see these again on another slide. So here's where they are. We have abstract object location and abstract object location 2D and 3D, and then we have concrete classes below that. So for example, here is geodetic 3D. And this class would contain 3 parameters for longitude and latitude and geodetic height. So one thing I hope you got out of this morning is that that's not enough. It doesn't tell you where you are, because I don't know if that latitude and longitude is on WGS 84, or maybe it's based on the Vancouver 2002 datum we just built. So this really doesn't show the whole picture. What happens is there are classes such as environmental route and property grid classes that specify what they're called spatial reference frame parameters that specify the specific ORM that these coordinate systems are built to. So typically, if you found this location, it was living below some hierarchy tree that came out of an environmental route, and in that environmental route you would see geodetic spatial reference frame parameters, which would say specifically we're using Vancouver 2002. Actually, you wouldn't see that because we don't support Vancouver 2002. But another difference you should be aware of, location 2D. From the point of view of the SRM, all location 2Ds live on the surface of the Earth reference model, some sphere or oblate spheroid. So all these, if you have a location 2D, that corresponds to something on the surface of the oblate spheroid. Now, people don't necessarily model that way. When people use locations for the nodes of features, they might want those things to lie on the topographic surface. So, you know, when they say this road intersection has a certain location, they'll give 2D coordinates, and they really mean it's on the surface of the ground. As far as the SRM is concerned, that's not where it is. The way we deal with this in the DRM is we have the ability in a class hierarchy to specify a reference surface. And the way we then interpret these locations 2Ds are, if there's no reference surface, then they're lying on the oblate spheroid. And if there is a reference surface, you take the location of the oblate spheroid, you take the normal to that surface, and you go straight up until you intersect the reference surface that was specified in the transmittal, for example, your model of the topographic surface, and then that's understood as where you meant location 2D to be. So it's a case. So there are many situations in which it's just tacitly understood you meant the topographic surface. In a SEDRIS transmittal, there's no tacit assumptions. You have to specifically say what it is, the surface you mean for these things to lie on. So I said, you know, we'd see these names before, and this just looks a lot like something we've seen before. So basically, what this is saying is we've pretty much implemented everything that's in the SRM. Notice that we only deal with spherical ORMs for these two cases. Okay, implementation of spatial operators. Transformations. Remember, a transformation is where you haven't changed coordinate systems, but you've changed Earth reference model or object reference model. We've talked about horizontal, basically the horizontal datums. That's where you've changed your oblate spheroid, basically. Not only its shape, but its position. And there's a limited support we're planning for these algorithms called 3-parameter, 7-parameter, and 3-parameter Molodensky. Ralph previously talked about the geoidal separation, the distance between a spot on a spheroid, oblate spheroid, and a particular geoid. If the spheroid geoid is WGS 84, which is a global datum, we produce the scalar separation. Remember, there's what's straight up on the spheroid is not necessarily straight up on the geoid, and that distance is straight up. We don't supply that. Here's how it's implemented in the API. All these functions have their special status codes, which tell you whether it's succeeded or not. And you essentially give it a coordinate in WGS 84, and it'll tell you what the geoidal separation is. And here are some of the status codes. It could say, I couldn't find the file, it has all this information in it, or it was successful. We talked about valid, extended, and invalid coordinates. Well, once you have them defined, we need support for that. Ralph's talked extensively about this. So essentially we have these three categories. Given a coordinate system that you want to apply a spatial operation to, which of these categories does it fall into? If it's invalid, then we don't want to do that operation. If you did the operation, you got something out, which category does it fall into? So locations may be referred to as being one of the three with respect to your starting spatial reference frame, and then when you do some kind of transformation or conversion or combination of the two, is your result, which category does it fit into? So a geodetic coordinate in Britain, if you converted it to UTM zone 17, it would be invalid because I guess that's nowhere near Great Britain. Defining where the extended coordinates is, Ralph talked about that, and it gets to be pretty complex, but it's in the SRM. Well, that's not quite true. Definitions are in progress, and it's partially implemented. There are transmittal validators that may use the check utility to determine whether a SEDRIS transmittal has locations that are valid or not. And data consumers have to be aware that the checking is something they have to do. Caveat emptor. The API will allow you to convert something if it falls in the extended region, but if it falls in the invalid region, it'll return an error message. This is what I mean by it will fail. The API will provide the support that essentially will let you make these distinctions, and so you can consume them properly. Implementation status. This essentially says that the transformation between here and here, wherever we see these symbols, the transformation is defined, but we haven't implemented it yet. And I don't know if this is this up to date, Michelle?
GCS geocentric does exist. That was added for this last round.
Okay, so we can erase that. That one's implemented. Okay. Local space rectangular had been floating around the other things because they are not tied to anywhere in space. But in the SEDRIS SRM, you can have a geometry model instance or a feature model instance in which you say, take this model out of the model library and plant it at this place in the environment. And if the coordinate systems of where you're planting it and the spatial reference frame where you're planting it and the spatial reference frame of the model are not the same, you have to be converted. An important case is the model that is built in local space rectangular, your usual XYZ axes that live in R3, not anywhere in the world. When you do model instancing for those, essentially what the SEDRIS SRM API is doing is it's creating a canonical local tangent plane at an appropriate spot, and it's doing whatever world transformations you specified, and then it's planting this, it's then embedding that R3 space or R2 space into that local tangent plane. So that's something which, in a sense, is outside the scope of the SRM, but it's certainly important in SEDRIS transmittals and using models. Coordinate operation chains. These are chains that have been optimized in the way that Ralph was talking about. Red means it's not yet supported, but that's probably, was it this one now is supported? Yeah, so you can go fix your printout. That is supported now. So these are basically the core of the API. You already saw geodal separation. These are the names of the other ones. We create a spatial reference frame parameter pair. These are the spatial reference frames you want to do an operation from and an operation to. And what operations can you do? You can change coordinates to the new SRF. That might involve a transformation. It might involve, it'll certainly involve a conversion, and it may involve both. You can do it for a single location. You can do it for an array of locations. And if you really know what you're doing and you trust your data, you can do it without bounds checking for speed. We also talked about directions and the operations you have to do on directions. So you want to, we have convert a direction, a 3D vector, or convert a transformation matrix. Essentially, if you take 3 orthonormal vectors and convert each of those, that will tell you what to do for a matrix. So this does it for you. And convergence of the meridian, the difference between a map projection, grid north, and true north. We talked about that, so that's supported. And then there's some memory maintenance, free resources that you use to do these computations. So here's the kinds of status codes that are returned. The operation was successful, or you never initialized your SRF parameters, or where you're going from or where you're going to is wrong. Well, you can read the comments. And more. The operation may succeed, but it's going to tell you that, oh, you're in an extended zone. You're not in the valid zone, so be careful. And, it could be an operation that we don't support. And you saw the little circle of slashes of the ones we don't support. There's more. And okay, these are for the vector and matrix ones. Gamma is for the convergence of the meridian. Geoidal separation, which we had talked about. Here's the operation setup. The first thing you have to do is create a parameter pair in which you have spatial reference frame parameter structures that tell exactly what your spatial reference frame source is and your destination. And that returns this coordinate operation parameter set pointer. And this is an opaque object which has to be used for subsequent operations. So here is a change SRF, and you have to then give it that pointer you got from the last call, give it your coordinates from your source, and it will return the destination. And these are the appropriate codes that could be returned. This does the same thing, but we're giving it an array. We're doing a whole bunch at once. Over here, the same two operations, one pair or an array of pairs, but we're not going to do any bounds checking because you're using trusted data or you think you know what you're doing, and so you're on your own. And then, of course, you want to free resources when you're done doing these kinds of things. And some of these are wrapped into other SEDRIS API calls. So, for example, as part of the DRM library, you can say, you know, I want to consume all locations in a particular SRF, even though the transmittal was in a different SRF, and the DRM API will use this API to make these conversions for you transparently. The vector operation one, again, we have a source vector, we have a destination vector, and what we tried to show you is that these are not, directions are not well defined unless you have a location where to reference that direction. And so we have to have a location coordinate as part of this operation. Same thing goes for a matrix. Well, I think that's wrong. We need a location there. I have to look into that. I may have copied it wrong. Convergence of the meridian. Rather than give you the angle gamma, we save you a computation and give you cosine and sine because that's what's going to be needed in subsequent operations. And this, with 5 minutes to go, is the last slide, so we can entertain questions. Yes.
Now that we've gone through all of this, okay, this is kind of a latent question, bottom line. In the SEDRIS for Managers class, they said that the SRM and I think the data dictionary one,
EDCS.
Yeah, it's a standalone technology component. Okay. Say, for example, now I have that standalone component that's at my office in my lab. Okay. And then now I'm saying, okay, I need to have a problem or something to apply using this tool. What I'm looking for is a simple example of running something through this SRM input and getting something on the outside.
Okay, the question is, how is this used in a standalone sense? I've been talking about some of the implications in using it with the SEDRIS DRM. But if we go back to here, these prefixes, SRM means they're all in the SRM API. This is the standalone part. They have nothing to do with the SEDRIS DRM. Okay, so this is, if you're doing something that is a standalone application, has nothing to do with the SEDRIS DRM, or maybe has nothing to do with EDCS, but you just want to use SRM, these are the functions you're going to use, plus the geodo separation one, which is not on this slide. And essentially, it's a case of, you know, what is your application? You have some map coordinates, and you need to get them into geodetic because that's where your dynamics are going to take place. Well, if that's the case, you will set up the pair to go between your map coordinates to geodetic coordinates, and then you'll make these calls. So this is the standalone part of the library. I hope that answered the question.
So I would need to know, my programmer would need to know the API piece.
Yes, and he would also have to know, for example, he's got map coordinates that say, you know, what a position is. He has to go find the little legend in the corner of the box to find out what datum that was built on. There are some things that he may be assuming that when it comes to using this API, you have to specify a spatial reference frame. So it's not good enough to name the coordinate systems. You're going to have to name which datum are you starting from, which datum are you going to. So he's got some homework to do, but it's all self-contained in the sense that only the SRM documentation has to be referred to. Any other questions? Oh, please fill out the questionnaires and take into account that we finished early.